Hi, my name is Alex, and for the Physics Lab 5, I chose to do the following Slinky lab. So the purpose of this lab is to model the motion of a falling Slinky, and then basically create a computational model of the motion, and then compare it with the experimental video. And so from that, we can determine the effects of gravity and the drag force on the Slinky's motion, and ultimately answer why the bottom of the Slinky remains stationary as the top is falling. So the key concepts for this lab are Newton's second law and the momentum principle. Basically, we'll use this to update the velocity and the position of the bottom of the Slinky in an iterative process. And then we also need to know just the force of gravity and the drag force. So for this lab, I just used the video of the falling Slinky that was provided, and I put it through Tracker to analyze the motion. And as you can see in the video, um, that's how I did. I basically took the point mass as the bottom of the Slinky. So the Slinky mass was 0.204 kilograms. Its initial position was basically around 0.000, and its final position was negative 0.523. The video was taken at 300 frames per second, and it was calibrated using um, Veritasium's height, which is around 1.75 meters. So once the experimental tracking was done, I created code to kind of reflect that. So we just basically, our initial conditions, we just put in the ball's mass, initial position, and initial velocity, which is 0.000 since it started from rest. Initial time, the change in the time, and then just our acceleration due to gravity, the direction that the Slinky is falling in, and then our drag coefficient. And then, so for the first while loop, we have to model the motion while the top of the Slinky is falling, but the bottom of the Slinky is still stationary. And to do this, basically the only forces involved are the force of tension in the Slinky and the weight of the Slinky. Um, so basically we have the force of tension is equal to the force of gravity, but opposite since the Slinky isn't moving. And then for the weight, we just have the the Slinky's mass times uh, the acceleration due to gravity, and then those added together are the net force. And then we can use the net force to update the velocity and the position using the momentum principle. And then for the second while loop, we model the motion of the Slinky as the bottom is actually falling. Um, and to do this, we have the drag force and also the force due to gravity. So we calculate the drag force and the weight of the Slinky, and then those added together are our net force. And then we again use the net force to update the ball's velocity and position using the momentum principle. So then for comparing the computational model and the experiment, both of the models basically have that this show that this Slinky is stationary until around 5 seconds. However, there was a large difference between the final heights of the bottom Slinky, and I think that this is probably due to just error in the timing and frames of the track of putting the video through Tracker, and then it could also be due to just um, human error in tracking the exact position of the bottom of the Slinky, and possibly calibration errors as well with Tracker. So then to answer the question, why does the bottom of the Slinky remain stationary? So while the top of the Slinky is still above the bottom of the Slinky, there is a tension force in the Slinky because the Slinky basically just acts as a big spring. And so during this time, the force of the Slinky, or the force of the tension in the Slinky, is equal and opposite to the force of gravity. And so therefore the bottom doesn't move. But then as soon as that um, the top part comes into contact with the bottom part, um, it's able to fall.